now we are going to lead compensation. So phase margin can be improved by reducing the magnitude of transfer function to lower the crossover frequency. We have seen what all the problems we have. That is going to be effective, but you have a lot of issues with that. So one alternative method is going to be alter the phase loop. Now alter the phase rather than the magnitude. Don't touch the magnitude, just alter the phase. So I'm going to add one network which is going to improve the phase margin. That is not going to disturb the gain of your network. So see here, instead of adding a capacitance resistance in series here, I am going to add a capacitance in the feedback path. So that is, you can see here, one capacitor is added in the feedback path. So as the frequency increases, the transmission through the capacitor will increase. So if you choose the capacitor correctly, it will ensure that you get the required amount of positive phase margin. But there is one problem with this. If you have a zero, which is also going to have a positive phase shift, and it pushes the crossover. So the point where the crossover happens is going to be pushed because of the zero. Both the pole and zero are going to provide a positive phase margin, which is going to push the crossover to a larger value. But unfortunately, when you have a poorly placed zero, the crossover will not be pushed so much, so that the when you consider uncompensated and compensated system, the phase shift is going to be relatively increased. So the net effect can be reduction in phase margin. So we have to be very particular about the position of the zero, because even though the zero is going to be poorly placed, that may affect the phase margin of your system. See, this is the loop function, and you can see R is parallel to 1 by SC. So the same previous formulas, there we use R plus 1 by SC. Here we use R parallel to 1 by SC. Other things are going to be as usual. So we have three terms. This is going to be the transfer function of compensator, and these two terms are going to cancel out each other. So you can see that the loop transmission 0 is at lower frequency than the lag compensator. And this lead compensator design is also somewhat slightly complicated, because we have to do a lot of iteration. We have to vary the zero location frequency and find the value where phase margin can be easily met. However, when you find the phase margin specification cannot be reached for any value of zero location, in such case, a combination, you have to go for both lead compensation as well as gain reduction. That case may work for many systems. If the necessary gain reduction is too large, then convert the gain reduction to lag network. Otherwise, you go only for lead compensation. So if lead compensation is going to work, you go for that. Or if it is not working, you use gain reduction also. If both are combining, you are facing issue, now convert the gain into a lag network. So you are going to have lead lag compensation. So you will have both lag network and the lead network, which is going to do the necessary work for you. The lead, again, to conclude, this is the case which requires ideal. Whatever additional networks you are going to add to your op amp should not disturb the functioning of the op amp. Okay, the forward block must have should not have a zero gain, and the feedback path should be providing the correct amount of negative feedback. You know the bandwidth is going to be power consuming and the price is too high. So this is a particular case of mechanical system where the power requirements are very high. Okay, so in large industrial machinery where the power and bandwidth are going to be very constraining factors, then careful design has to be done to ensure that this is going to be effective. So in electronic systems, large bandwidths are not always desirable. Noise is always present, and larger bandwidth means you are going to have more number of noise. So if this bandwidth is going to be excess, then there is unnecessary degradation of SNR. So signal to noise ratio degradation will be there, and if that is going to degrade, then the complete signal quality is going to be lost. So these are the different compensation techniques we have to analyze the stability of system. So all these techniques are focus on one thing: the phase margin should be positive, or if it is negative, you have to make it less negative. That will make your system even more stable. So this concludes